Discuss?
Yes, please. Yes, I hope I am audible. Hi, Professor. I hope I am audible.
Good evening, everyone. It is my privilege to introduce our speaker for this faculty development program. Today's session on AI-powered image processing application. And the speaker is Professor Shamik Tiwari. So please join me welcoming Dr. Shamik Tiwari, Dean and Professor at the School of Computer Science and Engineering, IILM University, Gurugram. Dr. Tiwari is a renowned academician and an accomplished researcher with over 2 decades of experience in teaching, research, and academic leadership. In 2023, he was recognized among the top 2% of scientists worldwide by Stanford University, a testimony to the global impact of his work. Dr. Tiwari's core area to expertise including artificial intelligence, machine learning, natural language processing, deep learning, and computer vision. His research has made a remarkable contribution to the healthcare innovation, especially in developing AI-powered diagnostic tools. One of his major accomplishments include leading a VIRAC DBT funded project that created a non-invasive diagnostic solutions for a diabetic retinopathy. Beyond this, his work has also addressed critical areas such as COVID-19 diagnosis and skin cancer classification, each of which bridges the gap between technology and human well-being. We are truly honored to have Dr. Tiwari with us today, and I am confident his sessions will inspire new perspectives in innovation-led education and applied AI research. Welcome to this FDP, sir. Over to you, sir.
Thank you, Professor. I hope I am audible. Professor, I hope I am audible.
Yes, sir, you are
Yes,
audible.
yes, sir. Audible, sir.
Okay. Thank you. Hope my PPTs are visible to all of you.
Yes, sir.
Okay, great. And let me check they are moving as well. I am moving to the next slides.
Yes, sir.
Okay, thank you. So thank you for inviting me for this faculty development program on AI. Yeah, title was AI application, image processing based AI application. Particularly, my title for the talk is AI for precision agriculture. So I am honored to be the part of this August gathering and the part of this FDP. Uh, I appreciate the efforts of organizing team to organize such a wonderful event, and with where the participants are gaining research and experiential learning, especially hands-on in the image processing and AI. So let me start what I'm going to cover in today's session. I am going to cover the introduction of AI. What is AI exactly? how AI can be used for the agriculture. What is CNN, convolution neural network? What is transfer learning? What is the use of transfer learning in learning? And some related terms related to when we are developing a deep learning model for some applications. My application is obviously agriculture field. Some data we have from the agriculture for leaf disease. So, but before moving to the experiments or the hands-on session, you should be familiar with few terms where I am going to cover data augmentation, data splitting, a gradient descent, some performance metrics. Then I have a sample data set which we are going to cover in this session, a sample code based on transfer learning, where we are using a pre-trained model to develop a model for a particular application in agriculture. And I will also show how to execute the code and how you are getting the results. So this I am going to cover in this session. So let me talk about the artificial intelligence. So as most of you know, when we mimic the behavior of human into the machines, then it is referred as artificial intelligence. So the exact definition of AI is AI refers to the simulation of human intelligence in machines that are programmed to think and learn like humans. So whatever human can do, and you mimic this behavior into the machines. Machine can be a system, a computer, or any hardware. Then it is referred as AI. Just for example, we are looking around us and we are recognizing what we have around us. And how this is happening, we are capturing the images around us or videos around us through our sensors. Sensors are our retina. We are passing those images or videos or whatever the data we are capturing through sensors to our brain. The brain is processing through the neurons, and then it is giving result to our organs. So we have different types of sensors. We have eye sensors to catch images and videos. We have audio sensors in our ears to capture the audio signals. We have different touch sensors in our skins. We can touch and feel. So we have multiple sensors in our body to capture the signals around us, passing to the brains, and brain is processing to those signals. So this is how what nature has given to us. And when we replicate this, the the efficiency or what you say intelligence given by the nature to the human being or any animal, then it is referred as artificial intelligence. So it is the brief, the history of artificial intelligence too long, but there are three milestones in the journey of AI. The first is the term AI was coined by John McCarthy at Dartmouth Conference, and the year was 1956. Though some discussion was there before 1956 as well, but the term is coined or again the attention after 1956. So John is also referred as the father of AI. So this was the first breakthrough in the journey of AI. In this journey, in 1997, IBM Deep Flu defeats the world chess champion Gary Kasparov. This was another milestone in the journey of AI. So once the Gary Kasparov was defeated by the IBM Deep Blue, the event has gained access or attention by the world. So this was the second great milestone in the journey of AI. And the third breakthrough, what I refer, is in 2012 when a deep learning model was developed with AlexNet and which won the ImageNet competition. This was, as per my understanding, was the third milestone in the journey of AI. And this was the era where the deep learning was gaining popular. It was gaining attention of the world. And after this, people realized that if you have the sufficient computing power, or what I say, infrastructure, you can develop a deep models which can work on a large amount of data and can be used, can be implemented for any computer vision problem. So this was the third milestone in the journey of AI. So as you know, there are three types of AI. The first one is narrow AI, general AI, second, and third is super intelligent AI. Narrow AI is specialized in one task only. For example, you are developing a chatbot, AI chatbot, like Siri or Alexa. So they are narrow AI, designed for a particular application. General AI, where human level intelligence across all tasks which are not yet achieved. So though few nature intelligence given by the nature are mimicked in the uh, systems, AI systems as of now, but still we have not reached that level. And super intelligent AI, it is theoretical, can be achieved in future, where AI can surpasses human intelligence. So we are not sure about this, but this is the third type of AI. So when you are in the domain of AI is not a single technology or a domain. It is a combination of multiple domains, multiple technologies came together to make intelligent machines, means AI. And the key technologies behind AI are mathematics, philosophy, computing, computer science, obviously programmings are required, and cognitive science. And AI can be divided into further categories as well. AI, machine learning is a subset of AI. So AI is a broader term. When you are designing, you are working with a particular kind of machine learning algorithms. They are referred as subdomain of AI, ML. And inside the ML, another subdomain is neural network, which can be used for supervised and unsupervised learning. And when you create a deep neural network, deep means you have larger number of layers, larger number of hidden layers actually, then it is a subdomain of machine learning or a subdomain of neural network. So machine learning can be of multiple types. Out of those types, neural network is a type. And when you have large number of layers in a particular neural network, it becomes deep in nature. That's why all those networks which are deep in nature and when you use them for learning purpose are referred as deep learning. So there is cross intersection between each and every technology. You can see here AI is broader, machine learning is a subset, and the subset of machine learning are reinforcement learning, unsupervised learning, supervised learning, deep learning, neural networks, transformer-based language models, GPTs, natural language understanding, computer vision, OCRs. So all those are the comes under the artificial intelligence. Now, so artificial intelligence, where you are mimicking the behavior of intelligence, human nature intelligence or human intelligence, and it has application in wide range of industries, wide range of problems, and one of the application of the AI is in for agriculture. So we are going to see few key applications of AI in agriculture. So AI is transforming agriculture by enabling smarter, more efficient, and sustainable farming practices. And few key applications are to monitor crop and the predict the crop crop production. So in this application, AI can analyze data from satellites, drones, sensors to monitor health, growth, and predict yields. It also enables farmers to make informed decision about planting, fertilization, and harvesting. Second is disease and pest detection. So computer vision and machine learning models identify early sign of crop diseases and pest infestations. It also allows for timely interventions, reducing crop loss and minimizing pesticides use. Precision agriculture, another application of AI in agriculture. So AI powered machinery and robotics enables precise planting, fertilizing, and harvesting. It optimizes input use of water, fertilizers, pesticides. It reduces waste and it increases yields. So this is why it is referred as precision agriculture, or precision in process of agriculture farming. AI can be used to monitor the soil and crop health analysis. It can be used for water management, so you can reduce the usage of the water for harvesting purpose. AI can be used for the benefit of the farmers, so they can do the livestock monitoring and upbreeding through AI-enabled cameras. Sensor track livestock health, behaviors, and breeding cycles. It can be used to enhance animal welfare and productivity, and support selective breeding programs. Predictive analytics and risk management. AI model forecast weather, market trends, and potential risks that help the farmers to plan and mitigate the challenges they face during the farming. AI can be used in supply chain optimization or supply chain management, where it can be used to optimize logistics, demand forecasting, inventory management, to improve the efficiency from farm to market, complete chain. AI can be used for automation and robotics. So AI-powered robot or drones can automate different kinds of activities in the farming, planting, weeding, and crop monitoring. And AI can be used for the market analysis as well. What is the requirement after 6 months? What is the possible price farmer can gain in the market? So that can be used for the benefit of the agriculture of the farmers. So this figure summarizes AI in agriculture. So robots are there to support the farming. Precision farming is there. Pest and disease detection is there. Soil health and monitoring is there. Better resource utilization is there with the support of AI. And it is predicted that by 2050, food demand will increase by 70%, and it is only AI which can support to reach to this milestone or reach to this requirement. Okay, so AI can be used in multiple ways in the agriculture, and one of the ways where a subdomain of AI, which is deep learning, can be used to predict, to recognize something. And there are multiple algorithms, architectures, networks are available in the domain of deep learning, and one of the widely acceptable, widely used, widely researched, widely popular architecture is convolution neural network. And most of us have heard about this network, that this is a network which can be used for computer vision jobs, where you can use for recognition, image recognition, or any kind of recognition. So convolution network are multiple types. Some they can also use for time series data. They can also use for 3D volumes. But here I am taking an example of 2D convolution network, which which can be used for recognition. In our particular case is the leaf disease recognition for the rice. So so moving to the experiments first, you should know what is convolution neural network. So you know what is neural network. Neural network is a network inspired by the neurons in the side the brains, and neurons are the actually a processing element which is getting some input, throwing the output, and in between they are doing some processing. So that's why it is referred as neural. So now neural are simply processing element, and when you have connection of multiple neurons or neurons, it is referred as neural network. So convolution neural network is based on the neural network, and in a ordinary neural network, additional layer is given from the domain of image processing, which is referred as convolution. So in the field of deep learning, the field of deep learning has appeared a lot over the past few decades due to the efficiently tackling massive data sets and making computer system capable enough to solve some computational problem. So as I discussed, hidden layers have helped in new era, with the old techniques being non-efficient, particularly when it comes to the problem like pattern recognition, object detection, image segmentation, and other image processing based problems. And CNN is the one of the most deployed deep neural network. So what is CNN? In the field of deep learning, CNN is amongst the class of deep neural network, which was being mostly deployed in the field of image recognition or analysis. And convolution neural network uses a very special kind of mathematical operation or method that is referred as convolution. And the mathematical definition of convolution is a mathematical operation being applied on two functions. So convolution is always between two functions. Function can be a digital function, means a matrix. A function can be analog signals. So function means two signals, or in domain of digital or discrete, it is they are the matrices. So mathematical definition of convolution is a mathematical operation being applied on two functions that give output in a form of third function that shows how to shape of one function is being influenced, modified by the other function. So this is a basic structure of any CNN. Any CNN. There are multiple kinds of CNN available these days. So, but you should, and all CNN have at least this part. The first is an input image. If you are in image processing domain, image recognition domain, followed by convolution layer. So input layer followed by convolution layer, followed by pooling layer, followed by fully connected layer, and finally output. So out of these all layers, the first few layers, first three layers are used for feature extraction. And the last layer is used for classification. Now you try to understand how CN is a shift from the ordinary image processing recognition methods. In ordinary image processing recognition methods, we do handcraft featuring, where it is the job of researcher or the inventor or the designer who is designing a solution to extract the feature and then pass to the some classifier. It can be a neural network, fully connected network. It can be any other network, or it can be any other classifier. Just for example, if we are in ordinary image processing domain and we want to recognize a car and the cycle, suppose two classes are there. So in ordinary image processing, it is our job, if we are designing the solution, to identify the features which can distinct the car from the truck. Just for example, it can be height, it can be weight, it can be number of tires, it can be size, it can be area. So all those features which can distinguish these two classes, we have to identify. After identifying, we will extract those features from those image sets, and then we will pass to any classifier. So this was traditional image processing. What happened with in the era of deep learning? This job of identifying handcrafted features is passed on to the uh, any architecture, any deep learning architecture. Just for example, in case of CNN, our job of identifying the features to separate to distinct two classes is given to the these three layers or the first part of CNN. So it is the aim job of convolution, pooling, and other non-linear layers to identify the features. Once features are identified, we pass those features to the network for classification purpose. So someone can ask why this deep learning was not popular before 2012. So this technology is not new. This architecture is not new. What happened when neural network was started in 1970? At that time, the infrastructure supports was not there. There was low memories in the systems. There was no idea of cloud infrastructure where you can have any size. You can demand for any size of computer infrastructure. So since the infrastructure support was very low at that time in that era, the deep learning or neural network could not gain popularity because they need a bulky amount of computational power to work upon. And in this era, you know, with you have no limit of computing power. You demand, there are cloud service providers who can provide. So even without buying, you can just subscribe the services and you can get any computation power for as per your need. And you need to pay only until you use. So that is demand based service. So CSPs are there, Amazon is there, GCP is there, Azure is there, and multiple private players are there. So once infrastructure is there, why should we do the tricky, a critical job of feature extraction? Let the architecture has to do this job. And that's why CNN and other deep learning architectures gain the popularity in this era. So sometimes we need multiple convolution layers, multiple pooling layers, multiple fully connected layer in any CNN architecture, and this diagram is showing this. So what is convolution layer? This is a first layer in any CNN that is responsible for the extraction of different features from the input image. The fully connected layer comprises the weights and biases together with the neurons, and it used to connect the neurons between two separate layers. Pooling layer. The pooling layer is responsible for size reduction. So since we are passing whole image to the CNN network, and suppose you are passing the image of size 256, 256, possibly there will be the features of size 256, 256. And out of those features, all features are not prominent to distinguish the classes. So we need to drop few features. That's why we have pooling layers to reduce the dimension of the feature space. We also need non-linearity in the network because the problems are image processing problems, are recognition problems are non-linear in the nature, and since they are non-linear in the nature, you have to add non-linear functions. They are also referred as activation function layers in the architecture. So there are multiple kinds of activation functions are there. Some populars are rectified linear unit ReLU, sigmoid, tanh, leaky ReLU, and others. And before moving to the how convolution neural network functions, you must understand what is the image and how image looks like. So there are three types of image usually we have. The one is binary image, where you have a single matrix. All intensities values are either 1 or 0, binary in nature. So once you will display such type of images, image will be a black and white image. Second type of images are grayscale images. So in grayscale images, we have different intensities in some range. For example, if you have an image of size 2 to power 8, so 256 intensities will be there, which will be the combination of black and white. So that's why they are referred as grayscale. But in terms of matrix, there will be a single matrix to represent any grayscale image. And third kind of images are color images. It can be in any format. It can be RGB, it can be CNBR, it can be multiple formats are there. And most popular format is RGB. So when you see an RGB image in a discrete or digital form, there are three matrices presenting three color channels, one for R, one for green, one for blue. So this is RGB image is displayed here in this image. So let's see how convolution neural network functions. So let we have an input image represented in the form of 0 and 1. We have a kernel. Kernel is a function, second function in convolution operation that we are going to convolve over the input image or the data. Kernel is also referred as filters or mask, or multiple names are there. So here it is a convolution filter or kernel. So what we do in convolution feature, we put the center of kernel over the image at some place, and the response at that place will be the sum of multiple corresponding values. Just for example, you can see in the figure. So one, the top left corner, 1 will be multiplied with 1. Output is 1. In the first row of in data, 0 is there. The first row of kernel, second column is 0, so 0 into 0, 0. Then 0 into 1, 0. Then we move to the second row. 1 into 0 gives you 0. 1 into 1 gives you 1. 0 into 0 gives you 0. So in this way, 9 additions, 9 multiplications will be there, and you will get the response at the center pixel. So a center pixel in the input data, which is 1 here, will be replaced by 4 after this convolution. And this process will repeat for each and every position in the input data. So this is referred as convolution. And convolution filter can be of any type. Depending on the nature of the problem, it can be designed. So this figure is representing where a convolution filter is convoluting over the image. I hope it is. What happened in the case of RGB image, since there are 3 channels, you are passing an RGB image to the CNN network, then that kernel will be applied separately on each and every channel, and result will be summed up. Sometimes your kernel or kernel filter can be different for each and every channel in the RGB image. So if you see this figure, we have separate kernels for each and every channel, red, green and blue. First channel is operating over the first image, first channel. Second kernel is operating over the second channel. Third kernel is operating over the third channel. And the output will be sum of all these widgets. So you can understand with this figure how kernel is working, convolution is working for a color image. When we are in convolution domain or Shannon domain, so when you are convolving a filter over an image, what happens for the border pixels? You do not have corresponding values to multiply. Just for example, if you see your filter here, the center pixel is 0, and when you convolve this filter over the top left corner pixel of the image, which is 4 in the image, and when you will convolve means you will put first, you can imagine the boundary pixels of 4 at top and left are zeros, means no background pixel is there. In that case, the corresponding value to multiply with the filter values are not available. So to resolve this problem, to do the convolution at the boundary pixels, there are the concepts which is referred as padding. So what we do in padding, we have multiple types of padding, and simplest is zero padding, where we assume that these are the background pixels, means you consider them as zero padding. We can have one padding, we can have mean padding, we can have duplicate padding, we can have mirroring. Multiple kinds of padding are there to overcome from the problem of convolution at the boundary pixels. Then you can understand this from figure, and then another term is there which is referred as stride. So usually we shift the convolution filter over the image by 1 pixel each time, but you can shift by 2 pixels, 3 pixels, depending on the requirement, and this shifting or movement is referred as stride. So as in general, stride is 1, we are shifting by 1. If you are passing 2 pixels, shifting by 2 pixels, stride will be 2. So these two terms we usually use with the convolution operation. So an example is given here where stride is 1, padding is 0, and total number of multiplications will be 4 into 4 into 3 into 3 for this image. Suppose you are using the stride of size 2. So in this case, since you are moving by 2, your 4 into 4 space will be reduced by 2, and it will be 2 into 2 into 3 into 3. These number of multiplications will be required to convolve a filter over the complete image. Padding we already discussed. You can always calculate the dimension after the convolution operation, and this is the equation to calculate the dimension of the feature after the convolution operation. Here you can see the function, floor function is there after calculation. So S is representing the size of stride, P is representing size of padding, F is representing size of filter, N is representing size of image. Some convolution operation over the volume is also possible, and this figure is representing convolution over the volume is 3D images or 3D space. Sometimes you can have multiple filters to convolve over the input data or the image. So as you can see from the figure, 2 filters are applied over the input data, input image, and the output will be the sum of those 2 outputs given by the response of first convolution operation and the response of second convolution operation. The total number of multiplication to calculate the result is 4 cross 4 into 2 into 3 cross 3 into 3, 864 multiplication operations will be there for this in case of two filters convolved over the image. One cross one convolution is also there, and usually it is used to merge the channels together. So a figure is representing this. So finally, to make a convolution layer, you have to add activation layer and a bias term that is represented in this figure. So you can see input image is there, two filters are there to convolve over the image. The two outputs are there after convolution. We have two outputs, so 3 cross 3 into 2 sizes of the feature space, and this feature space is passed to the ReLU function, which is a non-linear activation function. A bias term is added, and finally we are getting the output. So this is the overall picture of any convolution layer. So convolution layer is not just a convolution. To add the non-linearity and adjust the weights, a bias term is there, and then it makes a single unit of convolution. This is a shorthand representation of any convolution layer. A sample complete convolution neural network is provided here. For example, input layer 0 is there just to receive the inputs, no operation. And suppose the input size was 39 cross 39 cross 3, so RGB image was there, a 3D image was there. Then a filter of size 3 cross 3 is applied, a stride of size 1 is applied, no padding is used, so P is 0. Output feature space will be of size 30 cross into 30 cross into 10, because 10 filters are applied. For the next convolution layer, filter size was increased to 5, stride was increased to 2, padding is no change, 20 filters are applied, so the output will be of size 17 into 17 into 20. Then filter size was same 5, stride same 2, padding no padding, 40 filters are applied, the feature space has the size 7 cross 7 into 40, followed by a flattened layer. Flattened layer are used to make this feature space into 1D vector form before passing to the fully connected layer and the output softmax layer. So the flattened layer, where we have flatted 7 into 7 into 40, which is 1960, and we are getting. So pooling layer is very important here in any convolution neural network, not convolution operation, convolution neural network, to reduce the dimension space. And there are multiple two kinds of pooling popular in nature, which are max pooling and the average pooling or mean pooling. So what we do in max pooling, for the required window size, we select the maximum value. As you can see in the first figure, we have selected here 2 cross 2 window. So in 2 cross 2 window, first window becomes 4956. 9 is the maximum value. So this window will be replaced by single maximum value, which is 9 there. The next window is 2524, will be replaced by 5. Next window is 2456, will be replaced by 6, and then finally for 8. Similarly, in case of average pooling, the first window consisting of 4956 will be replaced by the average of these values. So average of these values, 4 plus 9 plus 5 plus 6 divided by 4 becomes 6. So it will be replaced by average of them. So this is representing how max pooling is working. So your filter window is moving to each and every value space, and then we are calculating the max. So max pooling always reduce the length. So after the combination of convolution layer, pooling layer, rectified linear units, bias terms, finally we reach to the fully connected layer, which is used for the classification. So as the name suggests, fully connected layer means or each and every neurons are connected to each other. That's why it is referred as fully connected layer. So, so first part, which is convolution, ReLU, pooling, are used to calculate the features. Then we pass these features to the fully connected layer. And these fully connected layer are responsible for classification. Finally, we have a softmax layer in multi-classification convolution in neural network. If it is binary, then we use the sigmoid. But in case of multi-class classification, we have no other choice. So we use softmax layer. So softmax is used in CNN to convert the network final layer logarithm into probability distribution, ensuring that the output value represent normalized class probabilities, making it suitable for multi-class classification jobs. So what is the function of softmax layer, which is the last layer of any CNN, multi-class classification CNN? Convert the output values into the probabilities using this mathematical equation. And then these probabilities can be used to label the input into a particular class. Just for example, if you see the probabilities here, the second has the largest value, 0.90. So 0.90 will be considered, the input will be considered as the second label will be considered as the second class label. Then you must understand what is transfer learning. So we discussed the architecture of CNN. The first part is feature extraction part, second part is classification, and then probability distribution for the labeling. So in deep learning networks, collecting a large amount of data when tackling a completely new task can be challenging, to say the least. However, obtaining satisfactory model performance, think model accuracy, using only a limited amount of data for training is also tricky, if not impossible. Fortunately, there is a solution that addresses this very problem, and it goes to the name of transfer learning. The idea is very simple. You can train the model with a small amount of data and still achieve a high level of performance. So as the name suggests, transfer. You are transferring the knowledge of one domain to another domain. For example, in your childhood, you start driving cycles. So you did cycling, and that cycling is used to transfer your knowledge when you start driving your two-wheelers. Similarly, if you know how to drive a car, you can use that knowledge, and it is easy to learn driving of a truck or buses. So this whole idea, which is inspired again from the nature, is referred as transfer learning. So what we do in transfer learning, we train a model on a particular data set for a particular problem, but that trained model can be used to tackle the problem of another domain by little learning and other things. Give me 2 minutes. I have urgent call. Just wait. Meanwhile, you can download the data set which we are going to use in the experiential learning or hands-on. I am sharing the link of data set so that you can download, and if you have some Python spider or available Python environment available in your systems, you can use. Otherwise, you have to use the Google Colab and you have to install the required libraries for the execution. So I got the link. I'm sharing the link. Meanwhile, you can review the data, and if you want to execute, you can download the data. Sorry for the interruption. I'm back. So I left at the transfer learning. I hope I am audible now. Anybody? I am back. I hope I am audible.
Yes, sir, you're audible.
Okay, thank
You're
you.
audible.
Thank you. Thank you. So, as we are going to experiment a transfer learning approach for the precision agriculture. So, you must understand what is transfer learning. So, transfer learning to utilize the knowledge of one domain to another domain. So, this can be used in deep learning era as well. So, what we do in ordinary learning or training, we learn from the scratch. A model without training, a blank model is there, and we train from the scratch. But what we do, as you can see in the figure, a pretend model which is trained over some data set, and this model can be used for the new job. And there you obviously you have to do some changes there. You have to fine tune, but that knowledge can be used for the another domain. Just for example, a data set trained on cat and dogs data set can be used for car and truck. How you will understand later, but that can be used. So usual approach, two models, separate models are there, two separate data sets are there, trained separately. But in transfer learning, a model 1 is trained over the data set 1, transfer the knowledge over the data set 2. Traditional learning system versus transfer learning. Now we are moving to the types of transfer learning. So transfer learning is usually expressed using pre-trained models, and this can lead to the faster training times and improved performance, especially when the second task has limited training data. So based on the transfer learning can be divided into multiple categories or types, and the first category is based on the data size. So you can see in this figure the type 1 category where you train the entire model from the scratch. Type 2, train some layer, frozen or leave, train some layer and leave, frozen others. Type 3, where you keep the full model freeze and feed the dense layer according to the classifier. So there are three types of transfer learning based on the data size. Whole model is freezed, half model is freezed, half or some portion of model is freezed. We are not going to train again, and complete model is trained again. So which approach we should use, when to use a particular approach. So you can see 4 quadrants are there. So train the entire model. When we should do this? When we should do this? We should do this when we have large data set but different from pre-trained models data set. Quadrant 2, train some layer and leave other layer frozen. So large data set and similar to the pre-trained models data set. Quadrant 3, when a small data set and different from pre-trained model data set, you train some layer and leave others frozen. Don't change. But quadrant 4 approach, where you freeze convolution base all layers, and this approach should be used when a small data set and similar to the pre-trained model data set are there. So data set is small and is similar, then freeze the complete convolution layers and then use. So a diagram for particular strategies where both base and classifier use frozen and unchained weights for the new classification problem. A dedicated classifier is proposed and trained on the new data examples, and part of base has unfrozen weights as well as dedicated classifier. So 3 strategies are discussed in these diagrams. So there are multiple transfer learning approaches. They include feature extraction, fine tuning. Then you should know what is data augmentation and how to use the deep learning models when you have limited data set. So data augmentation, I hope you know what is data augmentation. Anyone, please? Someone is familiar can.
It's actually to regenerate the same kind of images in order to increase the sample size so that the deep learning method would work, because deep learning methods require the huge amount of data and images. So
Perfect. So if you have limited data set and you have a network of a larger size in comparison to regular classifiers, you have to do something with the data set because your requirement is more. And when you do something with the data, something with the data means you are generating larger amount of data from the existing data. The technique is referred as data augmentation. So there are multiple approaches for data augmentation, and one can be you rotate an image, you scale an image. So if you are familiar with the computer graphics domain, there are multiple transformations are there: scaling, rotation, mirroring. All those transformations can be used for the data augmentation. So, so why there is a need for a large amount of data? So if you know these three networks, VGGNet, VGGNet was developed by the uh, Visual Geometry Group, a deep video network, or a GNMT network. A VGG network was used for identifying image category. Deep video network was used for video category, and GNMT, which is Google Neural Machine Translation, is used for translation. So if you see the output classes of these networks, the VGG net consisting of 1,000 categories, the deep video consisting of 47 categories, and the GNMT is for the text. If you see the parameters are which you use to train the network. For example, weights can be a filter weight or the weights in the fully connected layers. So those who are familiar with the neural network area, they understand the weights. So parameters are 140 millions in VGG net. There are around 100 million parameters in deep video. There are 380 million parameters for the GNMT. So with these large number of parameters, you can imagine the size of large number of output classes. You can imagine the large size of networks. And networks are so large, you need to have large amount of data. So अगर मैं हिंदी में कहूँ, अगर कोई भूखा है, ज़्यादा भूखा है, so these networks are hungry. Deep networks are hungry. They consume the data. एक बार आपने चला दिया और आपका डेटा नहीं है, you will not reach to the optimum result. खाना सप्लाई करना पड़ेगा, और वो क्या खाते हैं? दिखाते हैं इमेजेस, दिखाते हैं वीडियोस इफ दे आर डिजाइन फॉर वीडियोस, और दिखाते हैं टेक्स्ट डॉक्यूमेंट्स इफ दे आर डिजाइन फॉर द टेक्स्ट जनरेशन और टेक्स्ट समराइजेशन or any applications like ChatGPT. So state-of-the-art neural networks typically have parameters in the order of millions. Naturally, if you have a lot of parameters, you would need to show your machine learning model a proportional amount of examples and to get good performance. Also, the number of parameters you need is proportional to the complexity of the task your model has to perform. You can imagine. So data augmentation is a technique of artificially increasing the training set or data set by creating modified copies of data set using existing data. And you do just by minor changing. For example, you can see a single image presented in three forms. A ball is shifted, ball is rotated, not rotated here, but shifted at the two places. So to get the more data, we just need to make minor alteration to our existing data to make it larger. Data augmentation. So in interest of time, I'm not reading this, so you understand data augmentation. So there are two categories of data. Augmented data, which you augmented, you increase the size, and another is synthetic data, which is generated artificially without using the original data set, and it often use DNNs and GANs to generate synthetic data. So you must understand that augmentation is not only applicable for the images or image CNN. They can be used for variety types of data, including audio, video, text, or any other nature of the data. So why we should data augmentation? To prevent models from overfitting, to initiate training set is too small, to improve the model accuracy, and to reduce the operational cost of labeling and cleaning a new data set or raw data set. Multiple data augmentation techniques are there. If you are in the domain of audio data augmentation, the noise injection is there, shifting is there, changing the speed is there, changing the pitch is there. Text data augmentation, where word or sentence shuffling, word replacement, syntax tree manipulation, random word insertion, random word deletion. Image augmentation, geometric transformations, color space transformations, kernel filters, random erasing, mixing the images are used in image augmentation. So these are the different why we need data augmentation, how to do data augmentation, when to do data augmentation. Another important step when you are training or learning our deep learning model is data splitting. And most of you know, to avoid underfitting or overfitting, you need to have a generalized model. And for generalized model, to test the generalization power of a model, you divide the model data set into three categories: a training set, a validation set, and a testing set, to avoid underfitting and overfitting. So so I am not explaining in detail. So train multiple models, training data set, validation data set to validate the model, and testing data set to evaluate the model. Why we separate? That reason is important and you understand, but the reason we do this is very simple. If we would not split the data into different sets, the model will be evaluated on the same data which it has seen during the training. So we therefore could run into problems such as overfitting without even knowing it. So this is why we do this splitting. Usually we split the data set randomly into three subsets. They referred as train, validation, and test sets. Split size could be in ratio of 60-20-20 or 70-20-10 or any other ratio depending on your requirement and your desire and your results. We train the model using train set, obviously. During the training process, we evaluate the model on the validation set to know whether our training is going in the right direction or not. And we can adjust the hyperparameters at that time. Finally, after wrapping of the training, we evaluate our model on the test set. So if we are happy with the results, we can now again train our model on the train and validation set combined using the last hyperparameters we derived. So we do the multiple iterations, and we prefer those hyperparameters during training which are best on the testing data set. There are also cross-validation approaches where we split data set into different folds and we swap these folds, these subsets, also referred as k-fold cross-validation. So here k is 5. So the training data set is split into 5 and each and every fold is used for the validation purpose during the training. Then again, how to calculate after multiple folds? We do the mean or average of all performances. You should know how learning works during the training, and there is an important term which you should understand that is referred as gradient descent. Gradient means difference. Descent means you are reducing the difference, and this is the difference between your output and the actual output and the predicted output by the model. And this difference, the aim is to reduce this difference. That's why a learning algorithm which is used to reduce this difference is referred as gradient descent. So gradient descent is defined as one of the most commonly used iterative optimization algorithm of machine learning to train the machine learning and deep learning models. It helps in finding the local minimum of a function. So the best way to define the local minimum or local maximum of a function using gradient descent is as follows. If we move towards a negative gradient, means difference is in negative direction, or away from the gradient of the function at the current point, it will give the local minimum. Whenever we moves towards a positive gradient or towards a gradient of the function at the current point, we will get the local maximum. And our job is to optimize this to get the best optimal point. So the main objective of any gradient descent algorithms is to minimize the cost function using multiple iterations. In machine learning domain, in deep learning domain or neural network domain, we call those epochs. And the cost function is that the error between the predicted values and the actual values. And this error can be in terms of mean squared error, root mean squared error, or in any other form. So this is a cost function is defined as the measurement of difference or error between the actual values and expected values at the current position and the present in the form of single real number. So this is how gradient descent works. So we do not have enough time to explain this whole algorithm of gradient descent, but you can go through the PPTs I will share. And another term is learning rate, which you should know when you are in the domain of deep learning. A learning rate is defined as a step size taken to reach the minimum or lowest point. This is typically a small value that is evaluated and updated based on the behavior of the cost function. If the learning rate is high, it results in larger steps but also leads to the risk of overshooting the minimum. At the same time, a low learning rate shows the small step size, which comprises overall efficiency but gives the advantage of more precision. So there is always what I say trade-off between this or a challenge to decide the learning rate, the optimum learning rate. Both having a small learning rates have pros and cons. Both having a large learning rates have a pros and cons. And in both cases, it is you are not sure with which learning rate you are jumping the steps. So with which learning rate you will reach to the optimum solution. From the diagram, you can understand. So there is always you try a model based on different learning rates, and at some point you reach to optimum learning rate. This is the mathematical equation for the learning rate, and then you should also know the performance metrics. So after training is over, you test the model, you get the result. How accurate results are, that you should know, and you should calculate the performance matrices to know the efficiency of your trained model. There are multiple performance metrics. The first one is a confusion matrix. Those who are from the domain of machine learning, they know what is confusion matrix. So in the figure, you can see a confusion matrix for a binary classification problem, predicted versus actual. So if you see total samples were 165, out of 155, the no predicted 50, yes predicted 10, and others. So this is how we represent a confusion result in the form of confusion matrix. And from the confusion matrix, we calculate the true positive, true negatives, false positive, false negatives. And from these four terms, true positive, false positive, true negatives, false negative, we calculate the accuracy, we calculate the misclassification rates, we can calculate the true positive rate, which is also referred as sensitivity or recall. So this with one confusion matrix, how to calculate is provided in this diagram. You can calculate the false positive rate, you can calculate the true negative rate, which is also referred as specificity, and it is widely acceptable performance metrics in machine medical image processing, and we have precision as well. So these performance metrics can be used to evaluate the performance of any classification model. These cannot be used for the regression problem, where the output is continuous in nature, but for the classification where the output is discrete in nature, we can use all these performance matrices. So an example is given here. You can go through these PPTs later. All performance matrices are calculated. You can do your homework later. So now, after this theoretical foundation, what is AI? How AI can be used in agriculture? What are the different application areas? To know what is CNN, why we need transfer learning approach, what kind of transfer learning approaches we should aim for, in what scenario, and what are the some related terms like data augmentation, data splitting, learning algorithms in form of gradient descent, performance matrices. We are moving to the our experiential part, hands-on part, where you need to dirty your hands. So I have taken a data set for your understanding, a small data set, because when you run these algorithms or these deep architecture over a data set of larger size, you need to have a computational power. And since I am presenting through an ordinary system, which is a laptop, simple. I cannot afford a larger data set and a larger network. I have taken larger, but data set is very small, just for understanding. So I have considered this data set, which is a rice leaf disease data set. In this data set, we have three classes of leaf diseases. They are leaf smut, brown spot, and bacterial leaf. And these diseases are displayed in the slides. And data sets consist of smaller data set is of smaller size, consists of only 120 JPG images and 40 images in each class. So 40 into 3, 120 images are there, just for demonstration purpose, how we can implement transfer learning approach. I'm discussing code first, then I will execute. So this code first I am sharing. If you are with your systems, and all deep learning libraries like Keras, TensorFlow are available with you, you can simultaneously you can download the data and you can run on your systems, or you can use the Google Colab. So I am sharing the code. You can copy and paste in your Windows, and meanwhile you can execute. Oh, just wait. Okay, I cannot share with the chat box because I think has some limitations. So what to do? You can share the files. No, I hope organizer has shared the code with you. Link share कर दें. Link किसका करेंगे? I have in my laptop. It is not in Google Colab. So I can
will
do.
share in the group, sir.
Which group?
We have created one group, sir.
WhatsApp group?
Yes, sir.
Okay, let me check. I am admin.
I have created. I will share.
Okay, you please share. You share. Okay, fine, great. Okay, so moving to the code back. So the first part of the code where we are importing the libraries, you know what are the libraries? They consist of different library functions. So I use these libraries from different frameworks like TensorFlow, Keras, Skitlearn, Matplot, NumPy, OS. All these libraries are used. So you need to first job is you should know what libraries are required. And if you can see, in some cases, I'm not uh, loading the complete library in the environment. I am asking for a particular functions only. If you see the last line, from tensorflow.keras.optimizers import Atom. So this library consists of multiple optimizers, but I am interested only in Atom optimizer. That's why I wrote Atom. If you do not write, does not matter, but your environment will be unloaded by, it will consume more memory. So heavily loaded. So you must know what functions you need, that you need to import from a particular libraries. After this, in my code, which is shared to you, I have a data set. So I stored my data set in a folder, rice leaf diseases in C drive. So I have given a path, and I mentioned the classes in my data set. So if you have downloaded the data set, if you see the folder, there are 3 separate folders with these names: bacterial leaf blight, brown spot, and leaf smut. So 3 classes are there, and data set is into 3 folders. The image size, I prefer 224, 224. You can have any other size. So if the actual size is different, you will see the code next, where we are changing the size. So if suppose you have an image, actual image size is 160, they will be scaled to 224. If you have actual image of size 360, for example, usually we have in binary form, 2 to power form. But suppose you have 360, and then in case it will be reduced to the 2 to 4. So image size you have to take. Again, there is no standard what image size you should have. It depends on the bandwidth of memory available with you. If you have larger image size, obviously you need more memory to compute. Then I have decided best size. Best size in, suppose you have 100 images, you cannot load all the images at a time. Your memory will be uh, full, and your system will be hang. So we do it in batches. So I decided best size 32. So I will pass 32 images at a time. Once training will be over with those 32 images, I will pass other 32 images, and so on. And you can reduce this size, you can increase this size based on the memory available with you. Memory, obviously, main memory. Number of classes, I have used the length function to know the classes. So it will return 3 here. Epochs, number of iterations, I decided 100. You can have any number. The third part of the code is data augmentation and generator. So the purpose of this part of the code is apply data augmentations to the images to improve the generalizations, as we discussed. And we have data generators for training and validation sets with a 20% validation split. So if you see a particular block of data generator, we are rescaling, we are splitting 20% for validation purpose, we are rotating image 30-degree, we are shifting width-wise, we are shifting height-wise, we are shearing, we are zooming, we are flipping horizontally, and fill mode is nearest. So all these parameters are decided by me for this particular example. Then you can see train generator. So from where it is and getting the image, and validation generator is there. The next part is building a model. So a function I have designed here to build the model, a deep learning model for particular application where the base model trainable is false. So what I did in this code, you have to understand this part. Base model is my pre-trained model, which you will see in the next slide. So I have downloaded, I have accessed few pre-trained model. In this particular case, I have accessed VGG and DenseNet. There are multiple pre-trained models are available. So I used only VGG 16 and DenseNet. So those are my base model. I compared 2 models in this particular example. So base model trainable false. I am not retraining those models. The input is flatted. If you remember to convert the feature space into 1D vector, flatten. Passing this result to a fully connected layer, which is designed by the dense of 256 size, and activation function is nonlinear activation function ReLU here. After this, for generalization, we are also using dropout. Dropout is a function which is used for generalization, where we drop some percentage of neurons during training. So do not take the part. So here it is 50%, 0.5. Output layer will have 3 classes. So 3 activation function is softmax because it is multi-class classification. And the input for this model will be the input of the base model, and output will be output as in the previous line. So this function is designed to develop a model. So what we are doing, we are taking a base model, we are adding flatten layer, dense layer, and dropout layer in the existing model, and we are not training the existing model. So that's why base model trainable is false. So we are freezing the base model, no change during training. I have used 2 base models here, so you can see base BG16 and DenseNet 121. Weights are taken because they were trained over the ImageNet dataset. The top layer of these models is dropped. Why dropped? Because you can see include underscore top equal to false. Means we are dropping the top layer because in existing VG16 there are, I think, if I am correct, 42 output classes were there. So 40. So, but in this case we have only 3 classes. So that output layer is not required. So include top equal to false. We drop the top layer, and we added our layers which you saw in this code. So top layer is dropped, means classification layer from the existing model is dropped, and we added our layers flatten, dense, and dropout. Similarly, we have used another pre-trained model which is DenseNet. DenseNet has multiple categories, so a particular model, Dense 121, is used here. Then we build and compile the model. So we build 2 models. One is named as VG16 model. Another is named as DenseNet model. We compiled both models, and if you can see, the VG16 model is compiled with the Adam optimizer, and learning rate we preferred 0.0001. The loss function is categorical cross entropy because we have multi-pass classification. And if you have binary classification problem, you would prefer binary cross entropy. And the matrix during training, matrix is preferred accuracy. So this is the compilation steps. If you compare DenseNet and VG16s, total parameter in DenseNet are 8 million, around 8 million. But in VG16, there are 138 million parameters. Depth, DenseNet consists of 121 layers. VG16 consists of 16 layers. And other differences are given in this table. You can go through the later. So I discussed why we have include top equal to false parameter. What is input shape? We discussed why we are adding the custom layers in the base model. So we have 3 custom layers: flatten, dense, dropout. We are freezing the base model. I discussed base model trainable equal to false. I discussed how to compile. Adam is preferred here. And early stopping is also used in this particular code, which is shared with you. What is early stopping? If you see, I set the epochs as 100. Why I set 100 or I set to 500? Because when I begin the training or learning, I'm not sure at what step or what iteration I will reach to the optimum solution, reach to the right solution. So what we generally do, we keep initial epochs very high, but we monitor the progression of learning, which is in terms of loss or accuracy during the training. And if training is not changing, loss is not changing, or accuracy is not changing, for some steps we stop the training, even though we have given 1,000 epochs at the beginning. So this is why we use early stopping. And if you do not use, in spite of you reach the solution after 20 epochs, the learning will continue. Well, learning will remain continue for the 500 ebooks. So this is the beauty of early stopping. Then models are trained. The function is used here, fit function. So VG16 model dot fit is used for fit function, and we passed these parameters there: training generator, validation generator, epochs, callbacks, which is early stopping. Similarly, the DenseNet model is trained, and training history is stored in the two variables, VG16 history and DenseNet history. We are storing because we will plot these histories. Then next part of the code is to plot the training and validation accuracies during the training. So history is plotted in this particular piece of code. Then the models are evaluated based on confusion matrix. So confusion matrices are plotted by the code, and classification reports is generated where we have precisions, recall, and accuracy. So once you plot history, in my particular case, training was continued for the 35. Even I preferred 100 epochs in the beginning. So after 35, it was stopped because there was no change in the loss function. And this graph is showing the how validation and training accuracies are performing during the training. So if you see, you can see the difference between DenseNet accuracies and history of learning for DenseNet and the VG16. So these plots are also used to know whether model is overfitting or underfitting. The results are presented in the form of confusion matrix. Confusion matrix is of size 3 cross 3 since there are 3 classes. From the confusion matrix, these results I got, VG16 classification report. For example, for the vectorial class, precision was 86%, recall was 75%, F score was 80%, and support you can see, which is I have used 8 images out of 40 for the testing purpose, so support is 8. Similarly, the result for DenseNet classification. So if you want to compare these two models here, you can see the VG16 model is performing only 67, giving 67% accuracy. But on the other hand, the DenseNet is giving overall accuracy is 92%. So if you want to write a paper, a research paper, a research article, where you want to perform, you want to compare the performance of two transfer learning based approaches for the rice leaf disease classification, the findings will be the DenseNet is preferred because you are reaching to a accuracy 92%. So this is I'm throwing an idea to all of you. You identify the different problems. If you are working in a transfer learning domain, there are hundreds of pretend models are there. You compare, you design, you compare, and you identify a particular type of model for a particular type of application. And you should know that, for example, in this case, I am getting better result with the DenseNet, but possibly for the another problem, VG16 is giving more precise result, more accurate result for that particular problem. That is possible. So it is not 100% surety that this model will perform best all the time. No, depends on the nature of the problem. So this is your research. You have to identify. So presentation is over. I am moving to my spider window. I hope you can see my code. I hope you can see my spider environment.
Yes, sir.
Okay. So the code is pasted, and if you run this code, the training will start. You can see in this window at the right bottom corner. So my code generator has found 96 images belong to the 3 classes. Validation generator identified 24 images belong to the 3 classes. And then training is started. You can see, no, training is not started. It is downloading. No, yeah, it is started. Yeah. So first epoch is started for the first model, and you can see in the after first iteration the validation accuracy is 0.33, validation loss is 1.03. Training is continued for the second epoch. The validation accuracy is changed to 58.58 and loss is changed to 0.78. And similarly, it is repeating for the third epoch. So training is continued. So let's wait for the completion of the training, then we will see the results. Uh, Meanwhile, you can also run the code, and if you are getting some error, you can ask to me. So training has reached to 11 epochs for the first model, reached to 12 epochs. Let's see how long it will continue for the VG16. Training has reached to the 15 epochs. I do not know what is happening in your case because I am not getting any query with the code. So training has reached to the 21 epochs. So you can see Okay, so if you see the training of first model is stopped at 23 epochs. After the patience of 10 epochs, for last 10 epochs, there was no change in the accuracy in the loss. So it is stopped. But then the next training of next model is started, which is dense net model, and it reached to the fourth step. Okay, so training for VG16 model is over and training for DenseNet model is over. The results are displayed in terms of classification reports. So I have already discussed these results with you. Uh, so for VG16, we are getting 67% overall accuracy, for 83 for the DenseNet classifier. Uh, Variable Explorer, if you see, we have all these variables used in all these variables for our during execution of our program. If you see plots here, we are getting 5 plots. The first one is history plot for VG16, history plot for DenseNet, is confusion for VG16, and confusion for DenseNet. So this is how you execute code. But whenever you are executing the deep learning code, you have to install all these required libraries. And for example, TensorFlow, Keras, deep learning frameworks libraries are here, and rest are the usual libraries for the Python like NumPy, Matplotlib, OS. Uh, so I'm stopping sharing here. I hope you got the result, and In case of any query, you can speak. If you have executed this code, or if you try to execute this code, and you are getting some error, you can discuss. So yeah, so you execute later. Even in case of any issue later, you need any support, you can reach out to me. I'm sharing my mail ID with you. So if you have not executed, you can execute later and share with me. I shared the mail ID. Okay, great. I done from my side, Dr. Abhishek. Over to you. I am open for any query.
Ask question if you have. If there is no question, then we will bind up this session. We have still 15 minutes.
So, who has executed this code? Anyone from participants? If executed, can you share the accuracy for both the models? Because in neural network or in deep learning, if you execute multiple times for different systems, your accuracy will not remain same. Change because random in nature, because you're initializing the weights randomly. So even I executed 2 times, I got the different accuracies. So I would like to check what are you getting. I think none of you have executed or not reached to the solution. Okay, somebody is asking for the WhatsApp group link.
Sir, please read the mail carefully. We have already sent you all the links in the mail.
So it seems no queries there. You can bind up the session, sir.
Thank you very much, sir. For this particular session, we have learned different models. We have started with the CNN. We learned how to get pre-process our data, then define the model's parameters, then train the model. And if there are multiple models, then we have used transfer learning model to create something new for that particular data. So this session is very useful, sir. We have learned a lot, and I have shared all the codes and the PPT which you have given to me to the participant in their Canvas and as well as in the WhatsApp group. So they will go through from this particular code and they will implement. And the recording is also available. So I have shared these recording in Canvas. So thank you very much, sir, for this session. You can
Thank you for
leave.
your kind words and invitation. Thank you.
Thank you, sir.